it's getting to be time, so it's my pleasure to open this session D315 on engineering design case studies. And as we can see, we have 5 interesting case studies of engineering design to, let's say, get acquainted on. And so first we will have a look the videos that you have done and send it, and then during the videos I hope that you would write down your questions to the chat channel, and please indicate which author you are indicating your question, so that it will make it easier to discuss. And the first speaker, Michael, comes from University of Stuttgart, Germany. So I think we will see this video now. And meanwhile, you can keep your microphones off so that we don't create too much noise. Thank you.
Welcome, everyone. My name is Michael Voigt, and I'm very happy to present you the results of our contribution about the main characteristics of adaptive facades. Now, you're probably wondering, what is an adaptive facade? And to explain that, we will start with a conventional facade, as you can see here on the slide. The main functional task of a facade is to separate the outside world from the inside and to protect the interior from external influences, such as, for example, rain, radiation, heat, or wind. However, a conventional facade is usually planned or developed as a static facade, and any comfort deficits due to changing environmental conditions are compensated by the building's technical equipment. Compared to conventional facades, adaptive facades are characterized by being adaptable to environmental changes through their adjustable properties. Therefore, the demand for energy can be reduced as less technical building equipment is needed to optimize the occupant's comfort, as you can also see here on the right diagrams. On this slide, I just brought you 2 different adaptive facades. On the left side, you can see a shading system of the Alba Tower, and on the right side, you can see an adaptive facade that is adapting the ventilation. And while the right-hand side facade is a very technical adaptive facade with a control system, different sensors, and so on, the right-hand side is very, very basic in these terms, because it just consists out of wood that is swelling depending on the humidity. Focusing the research motivation, we have a relatively young technology with adaptive facades. In the year 2018, around 500 examples of them were built. And adaptivity raises, of course, the complexity of such a facade system, and therefore requires an interdisciplinary team. But in such a team, each stakeholder has different requirements and a different perspective on the design task. And when we look into the literature, the descriptions found there and the classification approaches there, they vary widely. So the goal of the current research is to generate a methodical support in terms of a consistent, more complete set of main characteristics of adaptive facades. And the subsequent research question is, what are the main characteristics of adaptive facade? Both interdisciplinary early stage discussion is key to identifying most promising design parameters. The research methodology chosen is that we start by analyzing classification approaches and descriptions of adaptive facades in the literature. We therefore did a systematic literature review in 4 electronic databases, and afterwards, to evaluate everything, support evaluation according to Blessing and Chakrabarty. The results are then 7,500 papers that were systematically filtered and then revealed 47 papers that suit our research question. Out of those papers, we identified 36 characteristics of adaptive facades, and as you can see in the matrix on the right side of the slide, there currently exist a lot of gaps in the classification approaches and descriptions in the literature. One main characteristic that we identified is, for example, the control system. So whether the facade is controlled by an additional system or whether the control is intrinsically integrated into the material. Those two differentiations we saw on the slides earlier with the two different examples of adaptive facades. Also interesting is the goal of the adaptation, the adaptive function, so the function that is realized as adaptive, or also costs and material. And as you already see, costs and material, of course, are characteristics that are relevant for more than just adaptive facades, but also for conventional facades. So what we did then, we filtered the characteristics, identified whether they are specific to adaptive facades or whether they are relevant to facades in general, and that reduced the amount of characteristics to a list of 17 main characteristics that are also specific to adaptive facades. And based on these criteria, we then did a support evaluation to check completeness, consistency, and logic. And therefore, in the first step, we had an expert interview with 12 experts where we basically asked them to describe adaptive facades based on main characteristics. And then we compared that to our list. And in the second step, we compared our list to 3 case studies where we first asked the architects and facade planners to name the relevant characteristics of their specific adaptive facade. These were then inserted into the table that you can see here and are marked in blue. And the second question was then to identify whether the characteristics that we found also play a role for their specific adaptive facades. This is marked in green here. And then we also asked whether some of the characteristics are irrelevant for their design, and these are marked in orange. And now what's very interesting at this point is that you can already see the design support that is given just by the list of different main characteristics here, because we can still see some gaps here. And these gaps are really characteristics that are important for their project, but weren't considered till that moment. So they weren't aware that this is a point they have to look at too. So to conclude everything, adaptive facades are a promising technology, but they are way more complex than conventional facades and therefore require methodical support in the design phases. We, for this, did a systematic literature review to identify 17 main characteristics that are specific to adaptive facades. And the support evaluation showed on the one side that we have a consistent, completed, and logic set, but also showed the first support in practice that can be given by the list. Further work will then deepen those main characteristics to identify already the solution space. So for example, when we have the main characteristic adaptation time, then there are facades that adapt in a matter of seconds, minutes, days, or seasons. That brings us to the end. I would like to thank you for your attention today, and I'm looking forward to the discussion round.
Okay, and our second paper also comes from Germany, from the Technical University of Munich, and it will be presented by Anand Vazhapilli, if I can pronounce it right.
Good afternoon, everyone. Welcome to my talk. My name is Anand Suresh, and I'm here on behalf of all my colleagues from the Technical University of Munich. The agenda is pretty straightforward. We start with the problem, and then we go on to explain how we solve the problem, and then we give a brief outlook and how we can do it better. Well, we need to understand robot operational complexity. Here on the left, you see a robot in an experimental setup, and on the right, you can see a commercial robot from Gardena used for mowing lawns. The user operational complexity varies greatly, and we try to reduce this complexity in this paper, and we do this by focusing on a trash picking robot. Another aspect is on how to improve empathetic behavior for these robots. Most of you might be familiar with the image on the left, which is from Boston Dynamics, where the robots are being kicked and pushed around. Those kinds of studies are very important to exhibit robustness of these robots. While a more interesting study is seen on the right by Tatsuya, where they study the behavior of children towards a humanoid robot in public space. They found the children to be particularly abusive and speculated that even though the humanoid robots were close to human likeness, it does not help in improving empathy. Instead, a better strategy is to elicit empathy in these kind of robots through design. We asked two questions. The first one being, how can we incorporate hardware design features that focus on human-robot interaction? And the second one being, how can the double diamond framework help to develop this robot? And just as a clarification here, when I talk about the double diamond framework, I would be focusing on the modified double diamond framework called Petra, as explained in one of our previous papers that you can see here. Moving on onto how we solve the problem, I would like to add a quick note that you can always see where we are in the double diamond framework on the top right corner of the presentation. We started with an ideation workshop to elicit our requirements. Here we can see that we listed several requirements and categorized them into what kind of functionalities we would like to have in the robot. We then try to categorize them into tangible and intangible development goals as shown here. Tangible development goals have specific technical attributes associated with them, while the intangible goals do not. We then took these different requirements and started storyboarding different concepts. We explored a number of different scenarios where the user has to interact with the robot in different settings. An example of this is shown here, where a cleaning services agency operator from Munich is trying to operate the robot in the English garden. Mood boards, which can inspire the designer and inform them on how to fulfill some of the intangible requirements. Here you can see some of the mood boards we used. We have elements across a wide variety of inspirations we got, such as from nature, their color palettes, texture palettes, and so on. We then take specific elements from these mood boards and try to sketch initial concepts of what our robot can look like. Equipped with our knowledge on what functionality we have in mind for the robot and how we want it to look, and how we want a user to interact with our robot, we then create multiple solutions for a specified number of tasks, and then select the best combination on how to achieve these tasks via a morphological chart, which allows us to do feature selection in a quantitative fashion. And then with this, we move on to conceptualization of the specific details and on how to design these different components or functionalities we want in this robot. At this stage, we are still exploring multiple concepts. And towards the end of the first diamond, we have a concrete solution in mind, and we have identified its associated components that would interact with the other components. But we are yet to decide on how to realize these components and functionalities, the technical realization. In the beginning of the second diamond, we look at different ways to realize our required functionalities and how to incorporate them in our design. This can be subject to availability of raw materials, compatibility, and know-how and timeline available to the team. And towards the halfway point of the second diamond, most of the components and functionalities and how to realize them have been concretized, and the design engineer then works on the integration design of these components. Finally, the robot is then assembled, and the second half of the second diamond is about integrating the robot and making small iterative corrections and doing a number of tests to validate our requirements. Here you can also see that the robot is then tested across different users, and the average task success rate for this was around 90%. Constraints, I will have to hurry through the outlook. On the first research question on hardware design features for HRI, you can see some of the outlook points here. Welcome questions on how to improve embodied cognition for HRI design and robots. While on the second research question on how the double diamond framework helped in developing said robot, this helped us a lot in assigning specific roles, in assigning a lot of specific deliverables, and etc. A complete list is found here. With this, I would like to close my talk, and I'm looking forward to your questions in the session. And here are my contact details if you want to contact me later. Thank you.
Okay, and our third paper comes from Japan, from Waseda University. It will be presented by Natsumi Hayashi, and I have pleasure to acknowledge that this paper has been reviewers' favorite, meaning that this paper has is among 10% of the best reviews in the conference.
Hello, I'm Natsumi Hayashi from Waseda University in Tokyo. In this talk, I'd like to introduce you a conversation tool that uses the property of ultrasonic waves to reduce conversational noise in quiet environments. Noise problems tend to occur in quiet environments such as shared rooms in hospital or evacuation shelters. In quiet environments, even small sounds and human voices can become noise. Common noise reduction measures include the installation of soundproof walls and the use of noise-canceling earphones and earplugs. However, these measures are difficult to implement in hospitals and shelters due to space, cost, time, and effort, and can lead to mishearing important messages. In this study, we investigate noise reduction for quiet environments where large-scale noise reduction cannot be implemented. The main principles of noise control are sound insulation and sound absorption. Sound insulation is to block sound waves propagating through the air with a barrier. The higher the surface density of the sealing material, and the higher the frequency of the incident sound, the greater the transmission loss. On the other hand, sound absorption is the attenuation of sound energy by converting the incident sound into thermal energy inside the material. Based on the principle of soundproofing, our research group considered the creation of a conversation tool with the following two features. The first feature is to reduce sound leakage to the surrounding by delivering voice only to the conversation partner. The second feature is to be able to be used in a way that hardly affects the user's posture during conversation. Then we focused on the parametric speaker. Parametric speakers have high directivity by utilizing the property of ultrasonic waves. We predicted that this directivity would enable the sound to be transmitted to a specific person. The ultrasonic wave has a high frequency, so it would be easy to block the sound even with the existing partition panels. On the other hand, it is necessary to take measures to attenuate the reflected sound. This is a conversation tool. A user supports the tool with one hand and speaks to the tool covering the mouth. The top part is a microphone cover with a microphone sensor inside. The cover has a curved surface to fit around the Mars. The bottom box in the main case, which include all the components such as the moderation, clavity, and battery. 20 ultrasonic generators are placed in the front side of the case so that the output sound travels towards the direction the speaker is facing. The cover can be dismantled from the main case, so the user can choose to hold the whole tool or only the cover. In addition, to reduce reflected sound, we made sound-absorbing material from newspaper and water. This material is placed in a net and is used as a cushion. The subject was then asked to listen to the recorded speech played through the conversation tool and sound-absorbing material, and a normal portable speaker as comparison. The tool or portable speaker was placed in front of the subjects, and 20 recorded words were played at each sound pressure. Subjects were asked to write down the word when they could hear it, a circle when they could hear the sound but could not understand it, and a cross when they could not hear it at all. The tool or portable speaker was used under 4 soundproofing conditions. First, not covered. Second, a cardboard box. Third, a cardboard box filled with sound-absorbing material. And fourth, a box filled with cardboard panels. Here is the result of the experiment. First, in terms of average number of correct answers, both the sound from the tool and the portable speaker were able to hear and understand the words when they not soundproofed. In addition, in all cases where soundproofing was used, the tool gave fewer correct answers than the portable speaker. This indicates that the tool is more effective for the same soundproofing measures. On the other hand, there is no significant difference between third, covered with sound-absorbing material, and fourth, corrugated board. The graph below shows the average number of respondents who answered that they could not hear the sound reproduced by the tool at all. This graph shows that the soundproofing measures using sound-absorbing materials are effective. Finally, here are some conclusion and future work. We have developed a conversation tool modulating voice in the ultrasonic range for soundproofing the French voice in order to solve the problem of conversation night in quiet environments. Experimental results indicated that the tools can be used right for conversation, and the sound leakage was reduced to soundproofing with cardboard and newspaper. For future work, we envision using this conversation tool in combination with sound masking to realize a more effective system that takes advantage of each other's strengths. Also, by integrating the tool and face mask into a single unit, we plan to lighten the tool, make it wearable, and easy for the movement of the head. This is the end of our presentation. Thank you for watching.
Okay, and again, our fourth paper comes from Germany, now from Leibniz University Hanover, and presented by Tobias Ehlers.
Ladies and gentlemen, I would like to welcome you to my presentation on design rules for laser beam melted particle dampers. First of all, I would like to start with a short motivation into the topic of particle dampers and their realization in laser powder bed fusion. Then I will discuss the research problem, the research objective, and my research question. Based on this, I will present my methodological approach, the results, and finish with a conclusion. As a result of increased sustainability requirements, which are more and more being tightened by politics, lightweight design plays a decisive role, especially through additively manufactured products. However, components designed for lightweight construction are increasingly prone to component vibrations. Here on the left side, shown in red, you can see a frequency response function of a weakly damped additively manufactured component. In order to reduce vibrations, additional mass must often be added to the system, which is in contradiction to lightweight design. Particle dampers, which you can see here, are a simple and effective measure for reducing vibrations in the field of lightweight design. Using additive manufacturing, especially laser powder bed fusion, particle-filled cavities, which you can see here, can be integrated into the component in one manufacturing step, thus addressing the effect of particle damping. This makes it possible to reduce components' vibrations by more than a factor of 20 in some cases, which you can see here in comparison to the red curve. The energy dissipation takes place through friction and collisions between the particles and the cavity. We already know from the state of the art that high and broadband damping can be realized by means of the effect of particle damping. The two most important design rules for maximizing component damping have been formulated as rules of thumb. First, the position of the cavities should always be in the area of maximum deflection, as this is where the particle dynamics are highest. Second, the cavity size should be maximized, as more particles can interact with each other. What we do not know so far is the precise prediction of the damping, either through simulations or experiments. The background to this is that the study so far, too few supporting points of the design parameters have been investigated to sufficiently characterize the nonlinear curves of the damping. The research objective for my work is thus to precisely characterize the effect of particle damping as a function of the most important influencing parameters: excitation force, cavity height, and cavity length. The final results should be design curves. My research question is consequently, how does the effect of particle damping behave as a function of the excitation force, cavity height, and cavity length? Next, I would like to discuss my methodological procedure for characterizing the effect of particle damping. Beams made of aluminium produced in the LPBF are selected as test object. The aluminium alloy was chosen because it is used in particular for lightweight components in the aerospace and automotive industries. The beams, which you can see here, have an outer dimension of 20 × 20 × 200 cubic millimeters and a cavity which is placed in the middle of the beam. The experimental setup is shown here. By means of an automated impulse hammer, which you can see here, the beams are excited to vibrate from 10 to 100 Newton, and the beam acceleration is measured by means of an acceleration sensor. The focus of the damping characterization is placed on the first bending mode, and the frequency range is evaluated using the circle fit method. The focus is on analysis of the influence of the cavity height and the cavity length, which are each investigated by 6 supporting points. In this way, the nonlinear influence of the damping can be mapped in detail. Due to the direction-dependent properties, the effect of anisotropy is also investigated by hitting the beams to vibrate successively in Y and Z direction. On this slide, I have shown the results of the damping characterization as a function of the cavity height. On the left are the results as a function of the excitation force in the Y direction, which you can see here, and on the right side, the excitation in Z direction, which you can see here. The cavity volume of 0%, which is here and here, represents the initial situation of the fully fused beam without particle damping. For the particle damped beams, the damping decreases with increasing forces, which you can see here. But the damping curve is approximately force independent for forces of 100 Newton and above, which is here. Thus, the influence of the cavity height for high forces is to be analyzed in the case of 100 Newton, which is this curve. It can be stated that the damping increases strongly up to 10% on the left side, and on the right side, the damping increases strongly up to 5%. And the damping is approximately factor 15 times higher than the initial situation of the fully fused beam, which is here. Beyond that, the increase in damping from here to here is significantly lower. The difference between the two figures of the damping curves at 5%, which is here, and here, can be explained by the length ratio of the cavity width to cavity height, which is 4:1. For an excitation in y direction, the particles cannot move as well as in the z direction. Finally, I would like to summarize my results. For the characterization of the damping as a function of the cavity length, I would like to refer to my paper at this point. With a cavity size of 2.5 to 5%, the damping can already be increased by a factor of 10 to 15. Strong direction-dependent damping properties occur when the cavity height is at least 4 times smaller than the cavity width. For this reason, a small cavity length and a large cavity cross-section should be preferred for small cavity volumes. However, the results presented here only apply to the first bending mode in beam geometry. It has been shown that the damping could be increased significantly, but further work should be carried out on durability tests, as the cavity could sometimes be a weak point. Thank you for your attention.
Okay, and now fifth paper, again, comes from Germany, from the Friedrich Alexander University Erlangen-Nuremberg, presented by Michael Jäger.
Hello, my name is Michael Jäger. I am research assistant at the Chair of Engineering Design at the Friedrich Alexander Universität Erlangen-Nuremberg. My topic today is the strength analysis of structurally optimized aluminium-composite tubular lap joints. I will start with a short introduction and a problem description, followed by presenting the analytical model and the design derived from it. After that, we will compare the design with numerical simulations and an experimental study, and finish with a short conclusion. Cross structures are very stiff, efficient, and lightweight, especially if composite materials are used for the struts. They can also be cost competitive to more common materials like metals if standardized profiles are used. The limiting factors of such structures are the load transfer elements, which are typically made of metal. Two types of elements exist: standardized inserts with a lower load capacity and more expensive customized ones with a very high load capacity. The goal of the study is to design structurally optimized and standardized inserts with a high axial load capacity. The analytical model used here is based on a single lap joint from Volkersen. It was adapted to suit the tubular shape of the joint. The limiting factor of these joints are the shear stress peaks at both ends. They have been optimized and two key components have been identified, which are the stiffness ratio of the joint partners and the overlap length of the adhesive. If you have a look at the diagram in the top right corner, the influence of the stiffness ratio is shown. By differing from an equal stiffness ratio of 1, the stress at one end of the joint is increasing, while the stress at the other end is decreasing. For an optimized joint, the stiffness of both partners should therefore always be equal. From the perspective of lightweight construction, the overlap length should be kept as short as possible. Let's have a look at the diagram in the bottom right corner. Here, the shear stress distribution is exemplarily plotted for several overlap lengths. The overlap length is compared to the so-called critical overlap length, which is determined by geometrical and material parameters. By increasing the length above the critical length, the stress peaks at the ends of the joints are no longer decreasing, only the stresses in the middle are further reducing. Therefore, the adhesive length has been determined as the critical overlap length. Now let's have a look at the optimized design. To ensure an equal stiffness ratio between both partners, there is no overlap between the adhesive part and the threaded portion of the aluminium insert. At points B, concentric surfaces for alignment and sealing have been added. Chamfers at point C, an undercut at point D, and a stop at point E ensure easy assembly. At points F and G, injection ports and vent holes have been added for the injection bonding process, which is used here. Additional radii at points H avoid stress concentrations. A comparison between the analytical stress distribution and numerical simulations is provided on this slide. The analytical shear stress is qualitatively correct, but is overestimating the stress peaks at the ends, while underestimating the stress in the middle of the joint. Therefore, it can be considered a conservative, safe estimate, which is consistent with statements on the literature on the Fulkerson model. In the Fulkerson model, the normal stresses are neglected, but the simulations show stress peaks at both ends of the joint. They are qualitatively similar, but significantly smaller than the ones predicted by Nemes et al. Due to the combination of the stress peaks, an early failure should be expected during the experimental study. The results of the experimental study are shown here. 3 different diameters in combination with 3 different laminates for the outer CFRP tube have been evaluated. A total number of 45 specimens, 5 for each combination of laminate and diameter, have been tested. The stiffness diagram shows a highly nonlinear behavior where a linear elastic result is expected. Above the predicted maximum elastic load, the behavior reverts to the one expected from a partially plastic adhesive joint. Considering the maximum load of the joint, the design exceeds the expectations. Almost all specimens reached a load where complete plasticity of the joint is assumed. For specimen with an inner diameter of 80 mm and D35 degree laminate, fracture occurred within the middle of the specimen in the laminate instead of the joint. Therefore, they are not considered. For a diameter of 26 mm and the 25 degree laminate, 2 of 5 specimens were outliers and were also neglected. Let's have a short look at the failure patterns of the joint. In almost all cases, cohesive fractures occurred within the laminate. This is illustrated in the picture in the top right corner. The innermost layer of the laminate is completely pulled out while still binding to the adhesive of the insert. To conclude the presentation, I will provide a brief summary of the topic presented. A design suitable for standardized profile geometries and with high axial load capacity has been derived. The failure occurs within the laminate instead of the insert. To improve common design guidelines, it is proposed to include material properties, especially when different materials are used. Additional guidelines could be: ensure equal stiffness between the joint partners. For lightweight reasons, using only 1 times the critical overlap length is sufficient. This differs from the literature, especially Habenicht, who recommends at least twice the critical overlap length to ensure full plasticity of the joint. Also, cylindric surfaces and stops are sufficient for alignment if winded CFRP tubes are used. Additional O-rings are not needed. Thank you for your attention. Are there any questions?
Sorry, Professor Ellman, there's some issue with your sound. You're breaking out. Can you check your connection? Okay, sorry, I cannot hear you. Can anybody else hear Professor Ellman clearly? No.
No, I have the same issue, but maybe you can be better.
It's a little bit better, but you are breaking out at the moment. So let's try like this.
It's still quite bad. Maybe the microphone has to
Can
be
you try
reset.
turn off your camera so that we can try to improve the internet speed on your side?
Yeah.
Yeah. No.
I think it's a microphone issue.
Yeah. We cannot. Professor Ellman, can you just press F5 on your keyboard and refresh your session. Okay, sorry everybody for this disruption. Hopefully we will continue soon.
So how does the Q&A work?
So can you hear me now?
Yes, now everything is
Yes.
perfect.
Okay,
Thank you very
good.
much.
Yeah, well, the system has some issue, not my computer, I'm sure. So can we go through the discussion starting from the first paper from the adaptive facades, which is quite fancy idea. So do you have questions for this paper?
I have a general question. Michael spoke about 17 characteristics, but then they were based on existing research, right? Is there something that, but he also spoke about characteristics that were left out. The first question would be were the ones that were left out based on the literature study that was made? And was there any other characteristics which is deemed important, maybe by architects or people directly working with the field, but it's not in literature, that can be included in this characteristic?
Sorry, we can't hear
Audio is
you.
also gone.
Miguel, can you also try to exit and enter the room again? Maybe that will solve the problem. Okay, Professor Ellman, it looks like Michael has some issues. Can we continue?
Yeah.
Hi, Michael. You are approved, but it looks like you need to refresh your browser. So please press F5, Michael. Sorry, we cannot hear you. We see you that you're in the room, but it looks like your mic is not on.
Oh.
Yeah, still no sound from you, Michael. You're probably using the wrong input. It's similar like at the beginning of the session. So try to use different input.
Yeah, it seems to me that this system has quite several this kind of errors. Okay, I hope you are back.
So, do you hear me now?
Yes.
Yeah, but it chose the wrong camera. So
it doesn't matter. We can hear you. That's the main thing. Yeah.
Yeah, just do it without the camera then. So the question was whether we asked some experts like architects and whether they confirmed our our characteristics, if I remember right. And we did this. This was a part of the evaluation. So we had 12 experts from different companies in the field of adaptive facades, and we asked them to just name or characterize or describe adaptive facades. And then we compared the characteristics that they have used with the characteristics that we found in the literature. And as we already used, from the perspective of the literature, as we already use the classification approaches and superior collections of different adaptive facades, there were no additional characteristics named by the experts that we haven't already found in the literature before.
Thank you. I was asking this because it seems like a pretty new thing, and maybe there are some invisible factors when it comes to morphing structures.
Yeah.
That's why I worked.
Of course, that's completely right. That's why I mean, you're never complete with such a set of criteria. That's why I always wrote like initial completeness, because we did the best we could do to validate everything in terms of a systematic literature review on the first place, then the interview with the experts, and then the third perspective with the different case studies where we asked them whether their characteristics are relevant. So that's, from my opinion to the moment, it's maybe all we could have done to somehow state that it may be initial complete, and then we will have to look whether further case studies that will be developed in the future may have additional characteristics that are important.
Yeah, and I think the main finding also was that you were able to discover some of the needs that the designers didn't notice at least with your method.
Yeah, exactly.
Yeah, and I think that's quite nice finding by you using your approach. I was wondering, let's say, when this kind of huge buildings have a lot of area in the walls, would the producing of electricity be one option on these facades?
Yeah, of course. So a lot of adaptive facades actually use some sort of working principle to generate or store energy from the sun. But just when you add like a photovoltaic element to your facade, it's not an adaptive facade. It's just a facade that is generating energy. But of course, you can combine those two technologies to already, or to also not just reduce the energy that is needed in the interior to get those comfort or to satisfy the comfort requirements, but also to generate energy that we would waste in other ways when we won't, if we don't use it, like for example with photovoltaics.
Yes, it's actually quite amazing what we can do with glass and some layers in the glass.
Yeah, exactly.
So, do we have some other questions for Michael? If not, I thank you, and maybe we go forward to Anand's paper about this trash picking service robot. So, questions, please. Very, very silent. So maybe I have some questions. So first of all, what did we learn about your study?
I think that comes to the core of the paper actually, and stuff that was not, I didn't have time to explain in this presentation, was that typically we break down requirements into tangible and intangible, and tangible are like product requirements you can write down specifically, but intangible requirements about how a robot should look and feel to elicit some kind of human response or empathy, or that promotes naturalistic interaction, like how you would with a living being. How can you evoke that in a robot, but then also ask these questions as part of the design process? That is the theme. And the framework on which we decided to try and implement this was the double diamond framework, where we are going through 2 stages of exploration, and then coming to meet at some tangible requirements. And what we tried to put in this paper was basically deliverables that makes sure that we think of this aspect of design too when you're making a service robot. So how to have certain deliverables, what steps to think of that can be integrated into the design process, and that helps you better design a service robot, basically.
Yeah, I was quite keen on your concept when you thought about how the robots should look like. So, for example, if it's humankind, look like people are considering, or children at least, considered it as some kind of human. But for example, if it's trash picking robot, should it look like more like hovering machine, so that people would acknowledge that, okay, what kind of machine this is?
It's actually a very interesting question, because this project has already gone into a commercial side, where the company is deploying it in cities, and they had to change how the robot already looks from this paper, because people were more aggressive towards it when we try to incorporate more human-like features in it. So because when you associate personality, I think it's also I referred a paper in the beginning from Tatsuya, where it shows aggressiveness towards anthropomorphic features in robots. We don't know what, I mean, at least I don't know what invokes this aggressiveness, but people seem to be a bit more aggressive when they think that it can evoke some emotion. So this paper did manage to, I mean, it was, the one aspect is how to make everything intuitive so you can interact with it better. And the other one is how to make it more anthropomorphic and elicit empathetic behavior. I think we definitely succeeded in the first part, where people were able to use it really well. But in the second part, it requires a long-term study, and now self-reflecting on the results we got over the long-term usage, I think we kind of failed there, because a more industrial-looking robot which can take the hits is much preferred to creating embodied cognition within an anthropomorphic robot. So this paper actually answered one question, but then still opens up another question, which is just a giant field that people are operating in HRI.
Yeah, I noticed that there were quite many things in your paper, but at least to my mind, this problem on how the robot should look like was quite interesting.
Yeah,
in the sense
that's why we focused on the usage, because the looks, I think we kind of failed, because empathetic behavior did not reduce violence towards robots.
Yeah, I think this is not really studied well so far, and I think at the future we will see quite many different kind of robots which are different kind of activities that they are doing, and somehow I think it would be nice to know what this robot actually is targeted for. So like I said, a trash picking robot might look like hovering machine, although it wouldn't operate in the same way. But it's quite much kind of psychological question, I guess.
Yes, because also these kind of robots, when they are roaming around in public spaces and they emote like a human, most people will just try to provoke it to see how it would react to.
Yeah.
So I think
it's a little primitive reaction from the people, because they know that the robots cannot really defend themselves.
This is actually what we also have been taught in robotics, to manage expectations, because once you project intelligence on a robot, people start expecting it to do things, and then they try to provoke it this way. But yeah, we were not able to address all of these different issues in a 6-page paper, so we tried to stick to the intuitive use cases instead.
Yeah. Okay. Do we have some more questions for Anand? Okay, thank you. Maybe we go forward and
Michael has a question.
Okay, yes, okay,
Yeah.
please.
But his mic doesn't work. Okay.
Can you type it? Okay, please type the question in chat.
Good question.
Double diamond framework and the V model. So the way we look at the major difference between the double diamond framework, so the one we use, the reason why we chose the modified double diamond framework is easier because we have a separate research line where we are trying to explore fuzzy front-end scenarios where we just have an idea of what requirements we should solve, but no idea how to go about it. So we are taking the perspective of complete novices coming into this. This is aimed at startups, student teams, where they do not know product development methodologies, for example, the V framework or the V model. So this is aimed at people like that. And we chose this modified double diamond framework because the way we have defined it is dialed towards prototyping, iterative development. While the V model doesn't exactly, even though you have some sort of feedback going through, it does not facilitate too many loops, and it does not facilitate for fuzzy front end. So when you have no idea what to build to solve a problem. So when there's this much vagueness in a product development process, V model does not allow for it. So it's more for use in prototyping. Exactly. So the way we look at this framework, the modified double diamond framework, is for reaching an MVP, a minimal viable prototype, which fulfills all the requirements. And then when you're trying to create a product out of it, then you go for more traditional methods of product development. This is for more exploratory cases, I would say, where a lot of prototyping and iterative development is involved. Thank you.
Okay, thank you. I guess we need to go forward because also our time is a little bit limited. So maybe we will now discuss about Natsumi's paper on this conversation supporting tool. So do we have questions for Natsumi? At least I have difficulty to understand the working principle. So I do understand how you can convert the voice to ultrasonic sound, but how people can understand, how people can hear the sound that is multiplexed on the ultrasonic sound.
Sorry, can you repeat the question?
Yes. So I didn't fully understand the working principle on how people can hear the ultrasonic voice or ultrasonic sound. Yeah.
出力音ってことか。The ultrasonic voice is a little not noisy. A little distorted sound. So we can understand the words, but it's not clear sound.
Okay. Yeah, I thought that this is not natural sound.
Yes.
But does it work somehow that because the human ear cannot really receive the ultrasonic sound, but maybe the bones of the head can receive it? Does it transmit like that?
Excuse me. I'm co-author of this Hayashi's work.
Yeah.
May I help?
Please. Yeah.
Yes. So when during traveling ultrasonic sound travels, ultrasonic sound. However, when the sound reached to the ear, the sound distorted, and we can understand the natural sound.
Aha. Okay. Yeah, this is neat finding, because basically then you don't need any device to hear it.
Yes, yes. Yes. Right. Yes. Yes.
Okay. Does anyone else have questions to Natsumi? This is like reviewers preferred it. That I surely understand, because this is quite amazing technology. I didn't realize that can be possible.
Sorry, I would like just a clarification. You have ultrasound distorted input, and then the output is clarified, or is it the other way around? Because when you speak about corrugated material as a medium, then I expect the sound waves again to get corrupted, right? So.
First of all, これでサウンドがさ、あれだと思って、媒体だと思ってますね。
Hello? Can I support again?
Yes, please.
Okay.
Yes. Corrugated board is just used for shelter. So in the evacuation center, we built some small shelter by using this corrugated board. So in the corrugated board shelter, people talk with each other by using this system. So corrugated board is just for preventing leakage sound.
For damping the sounds.
Yes.
But wouldn't the sound then be, let's say, corrupted because of the corrugated sheets? Because it can maybe dampen few frequencies depending on the corrugation material, or it doesn't matter. Maybe it doesn't matter if it's cardboard. I don't know.
The traveling sound has characteristics of ultrasonic. That's why the sound keep on reflecting in the corrugated board shelter. That's why we need some absorbing material.
Mm-hmm. Okay, I think I understand. Thank you.
Okay.
Thank you.
Thank you.
So, do we have some more questions to Natsumi? Okay, maybe we go forward to the fourth paper about this particle dampers, and by Tobias Ehlers. So that was also quite a nice invention, how this is possible. So when you say that you are targeting design rules, do you think that you actually achieved the design rules for designing those devices?
Hello, can you hear me?
Yes.
Okay. Definitely, that's not really a design rule, because for laser powder bed melted particle dampers, it's not so easy to characterize the effect of particle damping. That's not so easy. So I've tried to give a little bit more information how we can design the particle dampers. So my key message is that we can achieve a high damping with only 2.5 or 5% of cavity volume, a damping of a factor of 14 or 15. That is the most important information. Yeah,
I can see that you were able to show that they worked, they operate, and it's possible to do things like that. But I still think that it's a little bit some step away from real design rules if you want really design your device by using this technology.
Yeah, that's correct.
Yeah. Sorry to be a little bit critical. I should not be.
No, it's okay. Yeah, it's a little bit wording. Yeah, it's true.
Yeah. Do we have some more questions about this?
I think there are questions also from Philip and me in the chat. I don't know.
Okay. Sorry. Yeah. Yes.
Yeah, so let me start then. I was wondering, I look at your paper and you only have one cavity for this damping. Did you maybe try with different numbers of cavities or shapes of cavities? Because the title is design rules. So should we use only one cavity or multiple ones?
I only have investigated one cavity, but in the literature there are also studies with more than one cavity, and only investigated cubic cavity for my beams.
Okay.
And it's an interesting question, because when you have multiple cavities, you can realize a little fewer volume of the cavities and damping more modes than one. Because when you have a big cavity, you need more powder. And when you only want to achieve a high damping with 5% cavity volume, it is, I think, it is better to take 3 or 4 cavities and place them in the area of the highest deflection. That means for the first mode, you can put the cavity in the middle of the beam, and when you have the second and the third mode, you can vary the cavities or place the second and third cavity in the area where the highest deflection is. I think that is also a good solution. And I see the second question in the chat. That is a strength and stiffness question, because when I have one big cavity, the stiffness of the beam is not so good. So it is, I think, better for stiffness and damping design that you put more than one cavity in the beam, maybe 3 or 4, and then we have a good compromise of a high damping and a high stiffness and a high strength. So I would recommend this.
So what about the thermal effects of this damping? Because if you are, let's say, absorbing the vibration energy to these particles, I think they will heat up, and they will heat up your this device too. So would this be an issue?
I didn't have investigated this, but the literature said that the beam will be preheat of 2 degrees more when they are in the under vibration, so that's not so high temperature. So the particle didn't stick together. I have saw the beam in the middle and investigated the powder, and the powder didn't stuck at all. So it's that's not a matter.
Yeah, but I mean, how big the temperature increase might become? Would it 10 degrees or 100 degrees or just a couple of degrees?
Only a couple of degrees, only 2 or 5 degrees.
Okay, then we have some other questions.
Okay.
So from the Felix Enders, can you read it from the chat?
Okay, Felix, you need to press the blue button to share your audio.
Hi, I hope you can hear me now.
Yes.
Questions also to Tobias. First of all, we were already speaking about the shape of the cavities. Are you planning in your research also to optimize the shape, maybe, like for a maximization of the damping coefficient? That would be the first question. And the second one then, they were filled with the powder that you were also using for the printing, I guess. Are there also approaches to fill these chambers with different materials, which might even increase the damping coefficient too?
To the first question, I don't want to change the shape of the cavities, because when you have a cavity with a high dimension in the height and in the width, we also have to manufacture the beams, and We have in the additive manufacturing the 45-degree angle, and that is easier when I have a cubic volume. So I don't want to change this. But in the literature, there are also some investigations about a cylindrical cavity. But that is not really my research. To the second question, at our institute, we also have a multi-material printer, so we can print or leave unmelted powder with different powder inside the beams. That means when I have a beam made of aluminium, I can put inside the beam also tungsten. That is a material with a high density, and so I can also achieve a lot of more damping, which I cannot achieve with an increase in the cavity volume. That is also possible, but that is a really new technology. The alternative would be that I drilling a hole inside the beam and put the powder out and fill new powder inside the beam. But that is not so good with additive manufacturing. I think that are not the potentials here to put new powder inside the beam.
Okay, thanks.
Okay, thank you. I think we need to go forward because time is coming up, and we should go to the last paper by Michael Jäger about this tubular lap joints. So, can you explain what is actually the research question of this paper?
If you're using like the CFRP tubes, most of the weight is located at the joints. When you have to join these CFRP tubes together, you have to use like very labor-intensive manufacturing process if you want to laminate them together, or you just glue like metal inserts in it and screw them together. And then a lot of the weight is located at the nodes, which is not the idea of an fiber reinforced truss to have like a lot of you don't get that lightweight. If you optimize these joints, which are the main part of the weight in this stage, you can achieve like a lot of lightweight potential. And therefore we searched, or we had a look at these joints, because normally they were like, okay, you just glue something in there, you make it big and it works. But there are no like design rules how to get the dimension of these, how is the length, how are the inner diameters. Sometimes you have a lot of stiffness changes within the beyond the glue joint, and this all weakens the joint. So we try to get like a light component to further increase the weight of these truss structures.
Okay, do we have some other questions to Michael?
I have one question.
Okay, please.
I saw in this diagram that there was an inlet port on the CFRP. Is this to minimize friction? And the second one would be usually making any kind of holes or cuts on CFRP compromises on the strength. How do you manage that?
So the holes in the CFRP tube were for the injection bonding. There are researches in the literature where you can get like factor 1.5 to 3 more strength when you do injection bonding instead of like bonding then wet. So it's we are weakening the tube, but the CFRP tube at this point is not the relevant factor. The first part to fail is the glue joint, because they have a lot less strength than the tube itself. So it doesn't matter that much if you have like some small holes in there for the injection bonding. You can also get like, instead of 2 holes, one of the other, one on the one side, one on the other side. You can get several holes, and then therefore, of course, smaller ones, which don't have that much effect, but you also get the glue in there.
Thank you.
Welcome.
Some more questions for Michael? It came to my mind that, okay, this is the complexity of the problem in the sense that, okay, it's also quite, I guess, quite much material related problem. So that in metal part, like aluminium, you have different, let's say, blends of the material and also of the carbon fiber reinforced material. There are a number of different ones. So how you can take into account this material effect?
Yeah, that's one of our suggestions at the end, that we need to take these material parameters into account. This model here is based on, like, you have two materials with a different stiffness, but they are consistent along the thickness. If you have a look at a layered stiffness, a layered CFRP tube, you have different stiffnesses at different layers. And you use, like, if you're using the laminate theory, you have like a resulting one stiffness or one E-module. But you have to consider these different sites. We also currently working on using, instead of metal inserts, like short fiber reinforced inserts that were additively manufactured. And there you also get a lot of anisotropy in them, depending on the orientation you print them and the layout and so on. So that's some part of our current research.
Yeah, there I can see that there's some things to do for you. So, do we have still more questions? I think time is coming quite much up, but if not, I guess it's about the time to close this session. And I thank all the authors for writing these nice papers and also of this, I guess, quite good discussions. And I hope you all the best within your research work. So,
thank you very much. Thank you.
Thank you.
Yeah, thank you for hosting the session.